All right, guys, now we are in the final stretch of linear regression. So before I continue, just a little recap so that if you really want to know how to find the regression between two variables, right? I just click on stat and I go on regression and then click on simple linear. There's polynomial and other stuff, right? But that we won't talk about. So you can click on height and maybe weight in pounds or whatever, right? I can go ahead and compute it and you can get the StatCrunch output right here. So you can go ahead and see the regression equation is much more different than it was before, right? Here you have a negative y-intercept, so you can probably imagine that there's gonna be a little bit of hardship when you come to interpret this thing, right? And mainly it's because we only have 8 samples, so right? So if you look at it, right, this is what we get. Okay, so anyways, I'm gonna go ahead and exit this. So let's continue talking about effectiveness of linear regression, okay? So we talked about having two quantitative variables, and if they satisfied the assumptions, we can go ahead and do a linear regression model. We saw that there was some sort of errors in them, right? Unless all the points were on the same line, right? Then we will have perfect, linear regression, and everything will be beautiful. But that's not really how real life works. So my cat just got in the room. So if you hear random noises, then that's her. Okay, anyways. All right, so effectiveness. So how do we know that the regression is going to be good in terms of predictions, right? So there's other things that we can consider. So one thing is the residual plot. So residuals, what they do, they plot your x values and your residuals. So here, if you look at here, oh, what happened to my thing? Did it go away? Hold on. Okay, I think I fixed it. Okay, so if you want to go ahead and see the residual plot, right? So here's our studied, right? So as you can see, our studied is still here, right? Our studies on the x value. Our test grade is my y value, right? Now, the only thing that we do in the residual plots is the residuals are now plotted in the y value, right? So if you can see here, basically, let's go ahead and say what this means. Okay, so these are just our errors, right? So an error of 0 means that the linear regression model was exact. It exactly plotted the prediction matched up the true value. And as you can tell, right, when x was equal to 4, that's where it matched up. Here, there was a 0, right? So at x equals 4, there was obviously an error of 0. Our biggest error is probably these, right? Because this has an error of 15, right? So this corresponded with x equals 6, right? So it was probably something that looks like this. And as you can tell, this is much further away from the line itself, right? But basically, what we want to know is that what is a general pattern that we see in the residual plot, right? And in this case, we just see random stuff. We see a random scatter, and that is what we want. We want a random scatter. So if the linear regression is appropriate, there must be a random scatter. And as you can tell here, there really isn't anything out of the ordinary, okay? So let me go ahead and deduce a couple things. So if something is completely scattered, if our residuals are completely scattered, then in that case, we're perfect. Linear regression is appropriate. We can go ahead and use that. Now, there's two other things where it's not going to be appropriate, okay? And sometimes you will find this when you start graphing your regression. And then, or you look at a scatter plot and you see that there's outliers, or if you see that there's curvature, when you graph your residuals, that's when you're definitely going to see it. So there's two things that can occur. The first thing that can occur is this type of fanning type of thing. You see that there's fanning, right? So as x gets larger and larger and larger, your errors tend to be larger and larger as well. Whenever you see this type of scattering, of scattered, or increasing in the errors, is what we call heterokedasticity. So try to say that 10 times. So heterokedasticity is just fanning. There's fanning in the data. So heterokedasticity, that's what we want. What we want is homoskedasticity. Don't really worry about what they are, but just know that whenever you see a fanning type of shape, you know linear regression is not appropriate. So if there's fanning, if there's heterokedasticity, no, that's not correct. You cannot use linear regression. Whenever you see nonlinear patterns, like something that looks parabolic, some sort of pattern, right? Curvature, right? So this is more like if you see some sort of curvature, then linear regression is definitely not okay. We have to use some sort of polynomial, some sort of exponential, some sort of log, something completely different that's not linear. So remember, we only want linear regression. So if there's no linear if linear regression is not appropriate, it doesn't mean that you can't use anything with your data. It just means that you have to do something different. You have to do some sort of other model. Okay, so that's something that your residual plots can do. So if you go to and back into your data set and you want to access your residual plot, you click on stat, then regression, and simple linear. So it's the same thing, right? So here, hours studied, maybe test grade. And then when you go down here and graphs, you're going to see residual versus x values. You're going to click on that one and you're going to go ahead and compute. So everything is still there. It's not that hard to view. Here is basically all of your stuff, right? And then you're going to click on that. This is your residuals versus your hours studied. So this is very easy to access. Okay. Okay, so that's one way that you can see the effectiveness of linear regression. What you want is random scatter. We want random scatter. We don't want any heterosedasticity. We don't want any curvature. We just want no pattern. Now, why would it be no pattern? Well, think about it this way. What this is saying, having this fanning and type of pattern means that we are able to predict our errors, are random errors, and that doesn't quite make sense. In life, we can't really predict how much variability our errors are going to be because everything is random, right? What this is saying is that we are able to successfully predict our errors, and what we want is everything being scattered, everything being random. Okay, so that's just a little bit of intuition. Now, another way that we can go ahead and determine if linear regression is appropriate is something called the coefficient of determination. So what this does, it measures how much of the variation in the response variable is explained by the explanatory variable. Okay, and usually we say r squared. So yes, actually, r squared is just squaring the correlation. So if I square correlation, will give me coefficient of determination. So that's basically what it is. Now, what exactly does it do, right? And also square rooting the r is also going to give us r squared. Okay, so what exactly does it do? Okay, measures how much of the variation in the response variable is explained by the explanatory variable. Okay, so in other words, look at this one, right? Here, everything is explained, right? I can explain everything because I can, for any x value, I can correctly explain what the y value is going to be. So my r squared is just going to be 1. In other words, r squared is given to you in percentage, so this is basically 100% of the variation. I can go ahead and explain. Now this one means that I cannot explain anything because everything is just everywhere. So my regression line actually explains 0% of the variation. There is nothing that I can explain that's on this line that I can go ahead and say, oh, this is what it is. I can't do anything. Now, this means that only 50% of this entire variation can be explained by this regression, right? That's all it just means. So this is equal to 50%. It's a very, very vague concept, but that's basically what it is. It's how much of the variation itself am I explaining by the regression, okay? So this is basically how you're gonna go ahead and calculate it, right? One thing that you have to be very careful is when you wanna, if you wanna go from correlation to r squared, and you wanna square root the r squared, you have to have this plus or minus because remember r is between -1 and 1, right? That's what we have. But r squared itself is only from 0 to 100%, right? So we have to be very, very careful. Okay, so now let's go to these two questions and then we're done. Okay, so question 3. We conducted a regression for the width of books in terms of the number of pages. The correlation coefficient was r equals 0.9202. Find the coefficient of determination and interpret it. Okay, so I want to figure out what coefficient of determination is. So what is r squared? So if I look up here, in order for me to find r squared, I need to figure out what little r squared is. Little r squared. And I know what little r squared is. at least little r. Little r is 0.92, 0.9202, and then I'm going to go ahead and square it. Okay? So when I get into my calculator, I get 0.9202. I'm going to go ahead and square it, and what I'm going to get is 0. So round to three decimal places. So 0.847 approximately. Okay, that's what I get, which in percentage will be 84.7%. That is what my r squared is going to be. Now, what exactly does this r squared mean? This means that even though I don't know anything about the regression line or what it looks like, this tells me that 84.7% is explained. Oops, sorry, maybe that's not the way I should go ahead and describe it. Let me erase this again. 84.7% of the variation in book widths is explained by the number of pages. So in other words, I can go ahead and explain the variation, so variation in how scattered all these dots are, right? I can explain the variation of book widths by the number of pages, and the way that the only way that that's explained, well, I'm not making any sense. The only way that I can go ahead and explain the variation in book widths, right, with number of pages, is by the coefficient of determination. And the coefficient of determination tells us that 84.7% of it is explained, okay? Now, our last problem. Yay! Well, kind of. Okay, so given the following StatCrunch output, right, so now I give you a graph. If the coefficient of determination was 78%, find the correlation coefficient. Okay, so now we're going the opposite way. Now, if you remember, in order for me to find little r, the correlation coefficient, I need to take the plus or minus square root of the big R squared. Okay, so in this case, what is big R squared? That is just the 78%. So don't square it. It's still, but I'm going to write it as a decimal, 0.78, right? So that's one of the biggest mistakes. Just be careful. So let's take the square root of 0.78, and what I'm going to get is approximately 0.88. Now, at this point, we need to be very careful. This is not the answer. Is it positive or is it negative? Now, this is where you go ahead and look at your graph. Our graph shows a negative slope, right? So the correlation is going to go based on the slope of the line. And since the slope of the line is negative, we are going to choose the negative one. So this is negative 0.88. This is my correlation. So just be very careful when you're choosing the positive and the negatives, okay? All right, now the last thing, just before we finish, do not extrapolate the data, okay? Just in general. Extrapolation can be really, really bad, because if you have maybe from 0 to 100 pounds, right? And you have all your regression, right? Everything here, and I go ahead and have my lineup as fit. And let's say I wanted to go ahead and predict at 300. What's going to happen at 300? Well, don't do that. That's extrapolating. You are going outside of what the range is, right? And we don't know what's going to happen over here. We don't know if it's going to continue curving up. We don't know what the data is going to look like. So that's why we don't want to go ahead and extrapolate, right? So that's just something that you have to be very careful. And a lot of people want to do that, right? But there's other methods that you can do. There's ways that sometimes you can extrapolate depending on how much you're going off by the range of data, but there's other methods that you can go ahead and do if you want to know what, in terms of decision making, if you want to talk about decision making later on. But anyways, that's it for linear regression. We are going to do an activity on linear regression on our next class. So in the beginning of class, I'm going to go ahead and and do the quiz. So we are going to have another 5-minute quiz. And we are also going to talk a little bit about regression, just a little bit of review. Okay, and that's basically it.